Next ConvNet based model we shall be discussing is the Inception model. And the first version of the InceptionNet was developed in this paper entitled Going Deeper with Convolutions by Jegedi et al. The Inception model was a new state of art for classification and detection in the ImageNet challenge. The main hallmark of this architecture is the improved utilization of the computing resources inside the network, hence the term going deeper with convolution. So with this model, they showed how we could go deeper and increase accuracy without using too much computing resources, or better still, using the computing resources more efficiently. And this was achieved by a carefully crafted design that allows for increasing the depth and width of the network while keeping the computational budget constant. The most straightforward way of improving the performance of deep neural networks is by increasing the size, that is depth-wise and width-wise. By depth-wise, we mean increasing the number of levels, that's increasing the number of conv layers of the network, and width-wise, increasing the number of units, that's basically increasing the number of channels. And to increase the number of channels suffices to increase the number of filters. So this is an easy and safe way of training higher quality models. By higher quality, we mean more accurate models. But the simple solution comes with two major drawbacks. Bigger size typically means large number of parameters, which makes the enlarged network more prone to overfitting. Very important. The bigger the size of the network, the more prone is the network to overfitting. And if the number of labeled examples in the training set is limited, this can become a major bottleneck or a major drawback. And as we had seen before, to reduce overfitting, we need to increase the number of examples. But nonetheless, if the model is too big, overfitting can't be avoided. So this is a drawback, and we'll look at the next drawback. Another drawback of uniformly increased network size is the dramatic increase in the computational resources needed. For example, in a deep vision network, if two conv layers are chained, any uniform increase in the number of filters, that's to increase the width, reduces or rather results in a quadratic increase of computation. And worse still, if this added capacity, that's these added layers, are used inefficiently, that is, if most of the weights end up to be close to zeros, hence useless for helping the model in predicting better values, then a lot of computation is wasted. And the fundamental way of solving both issues will be by ultimately moving from fully connected to sparse connected architectures, even inside the convolutions. And so to resolve these two problems of overfitting and wastage of computational resources, the authors of this paper came up with the Inception model. So right here we have this naive version of the Inception model, where we have a previous layer and then the subsequent layer, which is gotten by concatenating these four different layers. So we have this sub block where we get a layer, we pass it through a 1x1 convolution, we get this output, pass it through a 3x3, get this output, here 5x5, we get this output, and here 3x3 max pooling, we get this output. And then from here we concatenate these outputs to now have the output of this block. And then this is passed onto another block or onto a usual conv layer. But as these inception models are stacked on top of each other, their output correlation statistics are bound to vary, as features of higher abstractions are captured by higher layers. And then the spatial concentration is expected to decrease, suggesting that the ratio of 3x3 and 5x5 convolutions should increase as we move to higher layers. So this kind of tells us how they came up with a whole inception model. But one big problem with the above models, that's stacking up these models, at least in the naive form, is that even a modest number of 5x5 convolutions can be prohibitively expensive on top of a conv layer with a large number of filters. So let's suppose we have this input 28 by 28 by 192, and then we have this conv layer which is 5 by 5 filters and 256 of them. Then from this formula we could obtain this output which is 24 by 24 by 256. And if we want to calculate the number of operations, we would have 24 by 24. First, because we have 24 by 24 outputs, meaning this filter passed 24 by 24 times on this input. And then we multiply by the number of filters. So basically this is like the number of times this filter was on the input, or we created patches on the input. And now for each of these patches we have 5 by 5 by 192 by 256 computations. Now the 256 is because we have 256 different filters, and this gives us 707 million operations. Now let's change or vary this naive approach. If we modify this naive approach, what we get is some sort of bottleneck right here. The aim of this bottleneck is to permit us reduce the number of overall parameters as we leave from this input to this output, while still maintaining the same dimensions in the output. So right here we have this 1 by 1 filter with 16 of them being piled up and passed is this input, and then the output we get is 28 by 28 by 16. And since now instead of having 28 by 28 by 192, we have 28 by 28 by 16, then the number of operations is greatly reduced when we pass this 5 by 5 filter. And with this, instead of having this 707 million operations, there is a great reduction in the number of operations. And that is how, instead of this naive approach, we now have the approach which was finally adopted by the authors of this paper. So instead of going straight to 3 by 3, we pass through 1 by 1 convolution, and instead of going straight to 5 by 5, we pass through 1 by 1 convolution. And right here we have the 3 by 3 max pooling with the 1 by 1 convolution after the 3 by 3 max pooling. And besides being used as reductions, they also include the use of rectified linear activations, which makes them dual purpose. So because we have rectified linear activations, that's ReLU activations, which are non-linear functions, after this 1 by 1 convolution, we're helping making our model more complex, hence can learn more features from its inputs. In general, an inception network is a network consisting of models of the above type, which is stacked upon each other with occasional max pooling layers with strike 2 to halve the resolution, that's to downsample the inputs. For technical reasons, it seemed beneficial to start using inception models only at higher layers while keeping the lower layers in traditional conv fashion. One of the main beneficial aspects of this architecture is that it allows for increasing the number of units at each stage significantly without an uncontrolled blow up in computational complexity. Another practical, useful aspect of this design is that it aligns with the intuition that visual information should be processed at various scales and then aggregated so that the next stage can abstract features from different scales simultaneously. And by various scales, we simply can see from these two images that with this smaller filter, we are able to focus on these regions where the objects appear smaller on the image. Whereas with this bigger filter, we are able to focus on this portion where the object occupies very large parts of the image. A particular version of this inception model is the Google LeNet. So Google LeNet is a combination of Google, since most of the research scientists worked on this paper were from Google, and LeNet is linked to Yann LeCun's LeNet paper. So it's sort of Google's LeNet. Now coming back to this, we have this initial, that's the input. We have the conv layer, which is 7 by 7 max pool, local response norm, conf layer, local response norm, max pool, and then right here we have this first inception block. So this is our first inception block, second inception block, third, fourth, fifth, sixth, seventh, eighth, ninth. So we see that we're able to stack these different inception blocks while ensuring that our model isn't overfitting and that we aren't using our computational resources inefficiently. On this table, we have details of the Google Net model or architecture we just saw, where we start with the conf layer, max pool, right up to the softmax layer. And then for each of these, that's for the inception, for example, we have all the different kernels and their numbers. So if we have this one by one, we have the number of filters, this number of kernels, number of kernels, and so on and so forth. This 3 by 3 reduce is the 1 by 1 filter or 1 by 1 layer which comes before the 3 by 3, and then this 5 by 5 reduce the 1 by 1 which comes before the 5 by 5. This is Boolean projection. This is the number of parameters and then the number of operations. Now let's suppose we have this input from this max pool layer, which is 28 by 192, and let's see how we obtain this 28 by 256 output after the inception 3A. So right here we have this 28 by 192 input, and then we pass this input through the max pooling of 3, strike 1, same pattern. Here 1 by 1 filter, strike 1, number of filters 16, same pattern, up to this 1 by 1, strike 1, number of filters 64, here number of filters 96. So these are the first intermediate outputs we get. Then from here we go after the max pooling, we add up this 1 by 1 filter, strike 1, number of filters 32, here number of filters 32, this number of filters 128, this is filters 5, number of filters 3, so this 3 by 3, 5 by 5, 1 by 1, and then this output from here is concatenated with all these other outputs to form this output. Now this is exactly how the concatenated output looks like. You find that this one, which is 28 by 32, is this, and then the next 28 by 32 this, then the next, which is from this 28 by 128, which is this, and then this other 28 by 64, and this gives us a 28 by 256 output. Since all these different outputs are concatenated together. And if you had noticed, there are also some auxiliary layers which have been added. So right here, after this concatenation, we have this average pool, conf layer, fully connected, and then the softmax activation. And this actually is similar to what we get at this output we have here. Now, let's reduce this by adding aux classifiers connected to these intermediary layers. We would expect to encourage discrimination in the lower stages in the classifier, hence they'll increase the gradient signal that gets back propagated back and provide additional regularization. So the aim of this auxiliary layer is for the purpose of regularization. So these two layers added for regularization. Previously, we had seen how to code out the whole VGG model. Now, for the inception, we shall just show how the block or the inception block is coded. Now we define each and every one of them. We have this conf or this custom conf layer, custom conf 2D, which is the conf layer with the activation ReLU and then with the batch norm. So this is the custom conf layer we have defined right here. And then we have this conf01, which represents the 1 by 1 conf layer, and then the number of filters is equals 64. So this is exactly what we found in the slides. And then for the next branch, we call it branch 1. We have the 1 by 1 followed by 5 by 5. Here the number of filters before this 5 by 5 is supposed 16. So modify this is 16, and from here we have 32. So this 32, and then coming into this 3x3, before the 3x3 we should have 96 filters. On the 3x3 itself we have 128 filters. So right here we have 128, and then after the pulling, and then so we have 3x3 strike 1, and then we finish up with this 1x1. Now let's take this filter to be equals 64. So that's it. So we've just built a simple inception block, and now we could call it by doing this. We have the each branch to get the input. We have branch 0, branch 1, branch 2, branch 3. So from this we get the branch 1, 2, and 3, and then we concatenate all those different branches to form our output. So basically this is how we build this block, and once you're able to build this block, you should be able to use the functional API to join all these blocks together. We also see how well this model performed as compared to the other models. So right here is first place, and then the top 5 error was 6.67. It should be noted that after the Inception version 1 was developed, there are other models or other versions of this InceptionNet which were developed, like Inception version 2 and Inception version 3.